welcome to my presentation. My name is Ali Yazdani and I'm a master student of artificial intelligence from Shahid Beheshti University. The topic of my presentation is emotion recognition in Persian speech using deep neural networks. I've divided my presentation into three main parts. First of all, I'll talk about speech emotion recognition or SER systems. Second, we'll look at different features that can be extracted from speech, as well as the two methods of extracting them. And finally, I'll show you the results we obtained in our experiments. I will also explain in details the deep learning models we used. So let's get started. As you know, speech is one of the main ways to express emotions. To obtain a natural human-computer interaction, it is highly important to recognize, interpret, and respond to the emotions expressed in the speech. The SER approaches consist of two steps known as feature extraction and feature classification. At the first step of speech processing, researchers have acquired several characteristics, including prosodic and vocal tract features. The second step is about using traditional classifiers, such as SVM or neural networks. Deep neural networks and convolutional neural networks provide efficient results for signal processing. On the other hand, recursive networks, such as recursive neural networks and LSTMs, are very effective in SER. So our main goal in this work is to investigate the different speech feature sets and their extraction methods, as well as the impact of using different deep neural network architectures to detect the spoken emotions such as anger, surprise, happiness, sadness, and neutral state in the Shemo dataset, which is a Persian spoken speech dataset. This dataset contains 3,000 semi-natural speech files. So that covers everything I wanted to say about SER systems. Let's turn now to speech features. As you can see on these graphs, in general, there are two steps to extract features from audio files. Initially, the audio file is split into smaller speech segments. The frames and the low-level descriptions or LLDs are extracted from each frame. Then different statistical functions such as mean, maximum, variance, linear regression coefficients, and etc. are applied to the LLDs to obtain a high-level or functional feature vector for each utterance. So different machine learning models such as SVM or decision tree can be used on functional feature vectors, or neural network models such as recursive or convolutional networks directly using LLDs. So in the figure above, we have an SER system that uses LLDs extracted from each frame, which are frame level representations. And in the figure below, an SER system that uses functional features obtained by applying various statistical functions to LLDs, which results in utterance level representation. So let's move on. It should be said that we extracted 52 features, including various spectral features such as centroid, contrast, roll-off, and bandwidth, along with features such as zero crossing rate and MFCC features from each frame as handcrafted LLDs. In addition, we tested two different feature sets for extracting LLDs using the OpenSmile toolkit. We also used three different functional feature sets for our experiments. Now let's move on to my final topic, which is the experiments. We tested and evaluated various deep learning models on the Shemo dataset. Also, we used various LLDs as well as functional acoustic features. The Shemo dataset is an imbalanced dataset according to the number of files in each class. So we used both unweighted accuracy and the weighted accuracy as evaluation metrics. Take a look at these tables. The results of our experiments are divided into 3 general sections. We first compared the results of applying different deep learning models to the features of handcrafted LLDs. The results show that the use of the LSTM recursive network on sequential LLD features have improved the model performance over DNN. It is also much more effective than LSTM alone in recognizing emotion in spoken utterances using the attention mechanism associated with BiLSTM. Finally, using convolution layers before BiLSTM with attention mechanism, more prominent components in LLDs were extracted first, which improved the performance of the model. It should be noted that this network in low resolution cannot have the same performance as high resolution because at low resolutions, convolutional layers cannot create effective representations of LLD properties. In second section, we test CNN plus attention by LSTM on 2 LLD feature sets extracted by OpenSmile Toolkit. As shown in table 2, this model still performs better on handcrafted LLDs than other feature sets. And in final section, we test different models of deep learning on functional features. The results show that using deep neural networks as well as larger feature sets can have better performance than traditional machine learning models. Compared to the traditional SVM model used in Shemo paper, 7% improvement of UA was achieved by using a simple CNN along with larger feature set. So that brings me to the end of my presentation. We looked at 3 main points. First, I spoke about STR systems. Then we looked at speech features. And finally, I explained our experiments as well as the results. To conclude, I'd like to say due to the novelty of using different deep learning techniques in Farsi, we introduced the best model for recognizing emotions in Shemo dataset. And finally, we were able to obtain higher accuracy than traditional methods. Thank you very much for your time. If you have any questions, please do not hesitate to contact us.